presentation comes from Department of Technologies, as you can see there. And the author and speaker is Brian Daly. And that's the title on an OX.
Thank you very much. Thank you. Well, it's great to be back here in Kentucky. I sense a lot of connections here. I used to be in the New York Club and knew Gary quite well. And of course, Leo and I used to do a lot of work when I worked for Degussa Fools, which is where I was for about 11 years. And of course, everybody knows Alex. And the thing that amazed me is he told me he got a direct flight today, or yesterday, from California, direct to Cincinnati. It took him 3 hours. I flew from Paducah to Memphis to Cincinnati. It took me 3 hours. So much for jets. What I'm going to talk about today is a new technology for synthesizing catalysts. I spent the better part of my career involved in really understanding catalyst synthesis. When I was at Degussa, it was a lot of precious metals on various types of powders, particularly carbon. I used to go around and try to preach that, catalyst synthesis is really a science, it's not an art, but it was always difficult to convince people of that. I think today, this methodology that I'm going to discuss, some of you may think it indeed is an art still, but we'll see. I'll go to the first slide, and I hope this works. I have a weak, there you go. Whoops, it worked too well that time. If you go to a statement at Vision 2020 a number of years ago, how the chemical industry needed to advance, a number of things were said, but certainly in the chemical synthesis area, it was specifically to develop new catalysts, in the materials technology area, new synthetic routes, or new synthetic techniques. And what I'm going to talk about today is what I think is a new synthetic technique for making catalysts. Specifically, I'm going to talk about some of the work we've done in the NOx abatement area. There's two general areas. There's the one associated with what Gary was talking about, NOx abatement for diesel. And then there's the other area with regard to NOx abatement for utility applications. What is the methodology that we have? Well, this little cartoon is a rough explanation. Basically, we take powders, finely divided powders, say for example of alumina, activated alumina, and some type of metal oxide. In the case of the NOx work that I'm going to talk about in the beginning, that metal oxide would be copper. And we physically mix these materials with colloidal metal oxides, acidifying them to promote a cross-linking process. Now, ideally, this might be what it is from a microscopic point of view, but from a macroscopic point of view, maybe it's something more like this. Again, these are cartoons. This is, to paraphrase somebody else, this is my imagination as to what we might have here. But indeed, some of the data suggests that we do create materials that have different porosities from the original materials, okay, different surface areas, and as you'll see in the presentation, different reactivities and thermal stabilities. Here's an example of a alumina composite. Here we basically have taken two actually the same alumina powder, and we've composited it with a colloidal alumina. And the difference here between these two materials is that in the case of material A, we're using acetic acid to facilitate the cross-linking process. And in the case of sample B, we're using hydrochloric acid. And you can see that there's obviously quite a difference between the surface area of these materials, and it's solely dependent upon the acid. Now, exactly what's going on here? Well, you might speculate that there's an effect with regard to the rate of cross-linking that's happening in impact. These are the kind of questions that we don't at the present time have the answers to, because, if I didn't mention, Apron, being a startup company, is anxious to bring new technologies forward. And so, to a certain extent, that sometimes means making and testing and not doing the kind of characterization work one should do. What I'm going to talk about now is specifically, I'm going to talk about the SCR work that we have done, specifically directed towards utility applications. I'm talking about coal-fired plants, for example. And as I'm sure all of you are familiar, the reaction chemistry is pretty straightforward. This is the case of ammonia as a reducing agent, reducing NO or NO2 to nitrogen and water. As I said earlier, again, we're just taking alumina powder. This would be, for example, alumina from Candia, say, for example, SCFA100, and copper oxide powder with an average particle size of maybe 25 microns. And we're using colloidal aluminum. In this particular case, we're using a colloidal aluminum available from Candia as well. And we're going to look at acids again, different acids, and see how this impacts on the performance of the materials. These reactions were all done in a tubular reactor, basically a quartz reactor inserted in a furnace. Mass flow control has allowed us to mix the appropriate ratio of gases, as you can see here, operating at concentrations of NO about 500 parts per million. The ammonia would range. The balance typically might be 1 to 1, but we did do studies where the ratios were as low as 0.8 and as high as 2.5. I'll explain why in a few minutes. Most of our reactions were done in the temperature range of 200 to 450 degrees centigrade, and most of the reactions that we studied, the catalysts that we studied, were done at space velocities of about 3,500. The off gas from the reactor was analyzed online using a FTR-IR. Basically, when we would do a reaction of one particular catalyst, that catalyst is usually in the reactor for about a week, allowing for at least a day to get to steady state, and then doing a number of tests in terms of looking at convergence as a function of temperature and ratio of ammonia to NO. Okay, here's an example of a catalyst. Again, whoops. It's an example of a catalyst where, like in the first example of the aluminum composite, here we're taking copper oxide and alumina, activated alumina, and mixing it with acetic acid. And you can see the conversion is, it's not too bad. You get about 100% conversion, and near that at around 325 degrees centigrade. However, if we switch from using acetic acid in the methodology to using hydrochloric acid, you see a significant enhancement in performance, where you can have almost 100% conversion at a temperature of approximately 250 degrees centigrade. I would like to point out that in the utility applications, the typical operating temperature is someplace around 350 to 375 degrees centigrade. However, in the applications for diesels, one of the things that you have to deal with is what they commonly refer to as light-off temperature. And ideally, they'd like to have light-off temperatures of at least 200 degrees. And what that means is you're getting at least 50% conversion. Of course, the process parameters are significantly different. Well, one of the questions one asks in a utility plant, there's a lot of things besides NO and ammonia that are in that gas stream. And of course, one of them is sulfur. So we decided we'll take a look at the catalyst performance to see if we see a deterioration if we expose the catalyst to SO2. And to our surprise, and I do add surprise because I spent a number of years doing methanol synthesis work, we didn't see a deterioration in performance. We actually saw an enhancement performance. As you can see here, at the high temperature end, where at 400 degrees we had seen a drop off from approximately 100 down to about 85. It was still at 400 degrees centigrade. At 400 degrees centigrade, it was still at 100%, and out to 450, still at 100% conversion. So it appeared that SO2 was not deactivating the catalyst, but actually acting as a promoter. In fact, here's another experiment where, again, we take the catalyst that was made using hydrochloric acid, and we subject it to SO2, and as you can see, we're running at about 100 parts per million. You see some uptake of SO2, then it seems to stabilize, but you see no loss in catalyst performance under these process conditions. So again, it suggests, and I only use the word suggests, that the catalyst does have some resistance to SO2 poisoning. One of the other questions that's asked many times is with regard to the thermal stability of catalysts. And in this particular case, what we did was we subjected the catalyst, again, this would be the catalyst made with hydrochloric acid. We subjected it to 700 degrees centigrade for 53 hours. Now, mind you, these catalysts, when they were prepared, after you go through the mixing process, there's a drying and a calcination process. And the catalysts that we had talked about had been calcined at 550 degrees centigrade. And what we saw was after we had subjected to this deactivation, and basically this is just in a muffle furnace being exposed to air, we saw that the activity was lower than it had initially been at this temperature 370. At 370 had originally been 100% conversion. But we saw with time on stream and SO2 in the feed that the activity gradually increased, and after approximately 100 hours was back to its original conversion level. Now, we're definitely curious as to what's going on here, and we've only just begun to try to characterize these catalysts to get a better understanding of how they're working and what are the components that are contributing to the enhanced performance. The first thing we can see here is that one of the things that we've noticed, obviously, sulfur definitely appears to be a promoter, and as you can see here, if you look at a catalyst without any sulfur, you can see that there's a direct relationship. As one increases the sulfur concentration in the catalyst, one sees an increase in activity. Now you might ask, well, how do I know that this ratio is 1 to 1 or 2 to 1? Okay, because I originally said that I treated the catalyst with SO2. Well, in this set of examples, what we did was a slight modification in the methodology. We basically incorporated in the methodology, in the mixing of the copper and the alumina and the colloidal alumina, we incorporated ammonium sulfate. Okay, and obviously, though that's different than treating with SO2, we still see the same enhancement. Now, one thing I'd like to just step aside for a second and say that one of the advantages when you look at catalyst synthesis on a commercial scale, okay, is that in a plant you have a lot of waste streams that you have to deal with. And in this particular methodology, if you've been able to visualize it, it's basically taking materials, putting them into a blender. And yes, you are adding some water to the process, but at the end, what you have is, in essence, a filter cake. Okay. That filter cake can then be shaped in any way that you want. If you want to extrude it into a monolith, if you want to convert it into pellets or tablets, you can do that prior to the calcination. And we've done that successfully. Well, a couple of other experiments we've done in trying to understand what's going on here is that we've done some ammonia absorption, desorption experiments using a Kahn balance. And briefly, we take the catalyst and subject it to helium at 400 degrees centigrade for several hours. Then we cool it down to 250 and switch from helium to ammonia. And you can see here, we get to about 20 minutes, we get what appears to be saturation. And then we switch the ammonia to helium. You see some loss of what may be fizzy-sorbed ammonia. But what you see here that's rather interesting is this is the alumina background. Obviously, you expect to see ammonia being absorbed by the alumina. But when you have the copper and then copper promoted with the chloride or made with chloride, you see a couple of things. You see what appears to be maybe a slightly higher ammonia uptake, but only slightly. But you see that a lower temperature required to dissolve all of the ammonia for the material that was made with chloride versus the material that was not made with chloride. So certainly there's some suggestion here that chloride itself is also playing a role, whether it's a case of it's impacting on the dispersion or whether there's some type of electronic perturbation that's having an effect on the interactions. Here, what we've done is a similar experiment, and what you see is that, again, looking at the alumina, now we're going to look at copper oxide that's promoted with sulfate, and then a catalyst made with chloride also promoted with sulfate. And interestingly here, you see that desorption of all of the ammonia basically occurs at about the same temperature. But there's a significant increase in the amount of ammonia that is absorbed for both samples compared to the original sample that was made with, without any sulfate. Now you might speculate that this is more related to the fact that you're changing the acidity of the alumina because you are incorporating some sulfate. And I will add that if we do a post-analysis of the material, we definitely do see sulfate present. Okay, the big question always is, how does this technology compare with the state-of-the-art technology in the utility applications? Utility applications right now, it's basically titanium, vanadium, maybe promoted with chromium, or maybe promoted with molybdenum, the kind of catalysts that are sold by Siemens and Haldo and others. So what we did was we tried to get catalyst samples of titanium, vanadium, but obviously we're not going to be able to do that. Proprietary technology. So we basically made titanium vanadium in the laboratory according to a recently issued patent. And what you see here is that conversion for NO is comparable up to about 375 degrees centigrade for both catalysts. As you get to the higher temperature, obviously the titanium vanadium appears to be performing a little bit better with regard to the amount of ammonia that's required to get 90% conversion of NO, and also I might add to keep the slip less than 5 ppm. Now what does that mean, the slip less than 5 ppm? If you're operating a utility plant and you have an upset, and so you're not generating as much NOx, you have a control system for injecting ammonia. Well, if the amount of NO decreases, then the concern is that you may get an emission of ammonia before your unit can react to change the rate of addition. And you can't be really above 5 parts per million without being having a violation, so to speak, with the EPA. But one of the things you notice here is, if you look at the difference between, say here at 350 titanium vanadium catalyst, you can operate at anywhere from 0.85 to 0.9 and not have an ammonia slip. Anything above 0.9, and you will then have ammonia in excess of 5 parts per million. This particular catalyst, the copper on alumina, you can operate again at a range of 0.85, but you can also operate as high as 1.45 and still not have an ammonia slip greater than 5 parts per million. This is extremely important to the utility companies. This is just another example of what I just said at 350 degrees centigrade. Okay. Some of you, I'm sure, I know Steve has heard this many times. That's great, but how does it really, it's great to see those kind of results in the lab, but how does it really work in the real world? And so, obviously, no one is about to spend $1 million to put our catalyst in their utility plant. But what we did do was we arranged to have a test, a field test, using what's commonly referred to as a mini reactor. This is basically a configuration. This reactor basically goes into a flue duct of a utility plant, and air comes through here, this eductor, and basically the flue gas is drawn through via venturi, and here's where you have your catalyst. Okay. The catalyst that we had, we basically were using ceramic monoliths that we got from Corning. These are 16 cells per square inch. You can see the configuration here. You see the blue coating, bluish-green coating. That's the wash coat that was applied to the monolith. This is another picture of the actual monolith. There were 3 of them, actually, that were inserted into this reactor. And here are the results. Now, I want to point out that this catalyst was only evaluated for approximately 1 day. Okay. But can see this is a calculated curve for a typical titanium vanadium catalyst. And what we're looking at is NOx conversion as a function of the ammonia to NO ratio at a space velocity of 11,000, which is significantly greater than what we had done in the laboratory. We've been operating at about 3,500. And you can see that the performance is comparable for that short period of time. Now granted, the next thing that we have to do, obviously, is to run this for an extended period of time. But an extended period of time is going to mean anywhere from 3,000 to 10,000 hours. Excuse me, hours, yes, right. So we're talking about a test, as Steve alluded to. This is always troublesome when you have to do this, but we're talking about a test that's probably going to last a year. And that's, it costs a lot of money to do that, needless to say. Just wanted to, a little sidebar with regard to NOx, because Alex had talked about some work done by John Armour and also in your lab with methane as a reducing agent. Certainly we're interested in looking at other reducing agents as well. And there's reasons for that, because SCR technology is being discussed and explored as a technology for diesel applications. I'm sure you wouldn't want to be driving your automobile with a tank of ammonium hydroxide, particularly in the winter up in Buffalo. But if there are other types of reducing agents that might be as effective, well, that's something to look at. And what we did was we again looked at our catalyst and compared it to the titanium vanadium that we had made. And we were using propylene as a reducing agent under these conditions. And interestingly enough, we do see that the catalyst is quite effective for reducing NOx with propylene, but also that performance is promoted when that catalyst is treated with SO2. To the contrary, when the titanium vanadium catalyst is treated with SO2, there's a loss in performance. This is another graph basically that shows similar. If you go up to a ratio of about 1.6 propylene to NO, you can get a conversion level of about 45%. Now this is just a quick study. Obviously this catalyst is not optimized for this particular application. Well, I'd just like to spend a couple more minutes and just give you some highlights on another area of NOx abatement, obviously three-way catalyst technology. I'm sure everybody's familiar with automobile converters, CO, NO, and some types of hydrocarbons. The hydrocarbons in the CO are acting as reducing agents for the NO. And of course, the typical catalyst today is basically your palladium-rhodium catalyst on a monolith, maybe 400 cells per square inch. It's applied as a wash coat, with alumina being the support. And there are a number of additives like lanthanum oxide, cerium oxide that are employed to enhance stability and performance. Well, we were interested to see how our technology would work if we tried to make a palladium-rhodium catalyst using an activated alumina, and then basically incorporating the promoters and also using a colloidal aluminum hydroxide. And what we did was, we made a number of catalysts. I mean, some were good, some weren't. And we had them evaluated by Southwest Research. These people are well known in the auto industry for evaluation of catalysts for many applications. And what I want to quickly show you is some interesting results. This is a reference catalyst. This is a commercial catalyst. Again, palladium-rhodium. And these were some of the catalysts that we made. The only difference between these two catalysts, again, was the acid that was employed. The palladium-rhodium ratios are the same as they were for the reference. The total loading is the same as the reference. The additives are the same as that were employed in the reference. And what you see is we're looking at steady state, and we're looking at fresh catalysts, and we're looking at light-off temperatures. And again, light-off temperature is where you get at least 50% conversion. You see that these experimental catalysts are exhibiting lower light-off temperatures than the reference, but only slightly lower. Nothing to really brag about. However, what you do see is interesting is after aging. This is an aging test that was developed by General Motors. It's a rapid deactivation test where the catalyst is subjected to about 965 degrees centigrade for approximately 24 hours in a gas stream. And what you see here is a significant loss in activity for the reference catalyst, where the light-off temperature after aging for NO is approximately 380, where originally it was about 280, a loss of about 100 degrees. You see in this particular case, this one catalyst, the light-off temperature for NO is only 300, where originally it was about 260. Now that's significant, because this means a lot of things in the automotive industry, and I'll allude to that in a minute, but let me just look at the next slide. Here we talk about conversions, because conversions are also important. Obviously you'd expect that if you have a lower light-off temperature, you might expect a more active catalyst. And again, you see that when you look at the fresh catalysts, yeah, these catalysts, these experimental catalysts appear to be more active, but look at the difference after aging, where, again, in the case of the NO, you see a conversion of about 27% for the reference catalyst after aging, and this one catalyst is at 50% conversion. So that's significant. What this suggests is that this method of synthesizing catalysts does seem to have an impact on the thermal stability. We saw that in the copper oxide catalyst, and definitely we're seeing that in the automotive three-way catalyst. Well, in closing, I just want to say that, you know, we are trying to develop new catalysts, and we are trying to explore new synthesis methodologies. And again, I think that we're onto something. It just depends upon where it's going to take us. I'd also like to acknowledge the people that involved in this work. Dr. Svetlana Areskia is a member of my team. She's done all the NOx work at Clark Atlanta University, working with Professor Mark Mitchell. And a lot of the three-way catalyst work was done by Dr. Ron Kears in collaboration with Gordon Bartley, Southwest Research Institute. Thank you for your time. Be happy to answer any questions.
Questions? When you put copper oxide, acid, and your colloidal alumina together, copper oxide will dissolve in acid.
That's right.
So presumably what you're doing is redispersing your copper oxide and allowing it to interact with the colloidal alumina, and then putting it down as small copper oxide particles on the alumina. Is that?
That's a possible explanation. Certainly, we, with limited resources, we do believe we've done some, microscopic studies, and we see that certainly copper oxide with using acetic acid, you see large agglomerates of the copper metal. If you look at with acetic acid, hydrochloric acid, the particles are much smaller. There's no question. And I will add that we've done other studies with other precursors for copper. And certainly there's a suggestion that the smaller the particle size, the greater the reactivity. No surprise. So it appears though that might be what's going on, but it still remains to be seen.
So why not go all the way and take copper chloride and put it in with your colloidal alumina and get full bang?
We tried that. Doesn't work quite as well.
I see.
We have tried other types of copper salts that work better
Uh-huh.
than this, but we have tried copper chloride and it doesn't work quite as well. There's two schools of thought, even within the group. My first reaction was we're just enhancing the dispersion. Some people still think that the chloride is acting as a promoter, because you do see residual chloride in the catalyst. So we're trying to collect a lot more data, and Dr. Reskia will be making a presentation at the Toronto meeting, where she'll have a lot of data. I don't want to take away her thunder, so to speak.
The way, from what I understand, you're making this is you're taking small alumina particles and small metal oxide particles in the presence of colloidal alumina. When you're making a wash coat on a monolith, is that the way you're applying the wash coat? Are you actually making the bond between the wash coat and the monolith with this colloidal alumina? Or do you prepare it first and then attach it to the monolith?
prepare it first.
Okay.
So the colloidal alumina is not going to be acting as a binder to the monolith.
Well, that was my question.
Right.
Do you get a better binding if you would do that? Because I guess my understanding, I don't know much about it, is that one of the problems with a monolith and a wash coat is that the probability the wash coat falls off the monolith.
It falls off most of the time if the support for the wash coat is different from that of the monolith. In other words, you got to deal with the coefficients of thermal expansion. And so if you have alumina versus the ceramic, the coefficients, the differences are small. So usually you have cracking on wash coats when you go to thermal excursions beyond what the catalyst is supposed to operate at. If you use a wash coat which was titanium based, then you'll have serious issues if you go to temperatures above 600 degrees centigrade. So in this particular case, no, we're not using colloidal alumina to try to bind it. However, as I said earlier, one of the nice things is that you can take the composite before you calcine it, and you can shape it into anything you want. And we've actually made monoliths with 400 cells per square inch, and it works quite well.
When you start, you see that the larger crystal size of copper oxide, but on the catalyst, do you see copper oxide crystal and larger crystal size, and do you see the copper chloride, or you see mixture of a copper oxide, copper chloride, or see amorphous?
Well, if we do an X-ray diffraction, we see basically amorphous. However, which again alludes to the fact that you have small particles. However, we are doing some IR studies as I speak, and we are seeing different oxidation states of copper. But I can't go beyond that right now because I don't have all the data. So it's a complex system, but it's like I used to, when I was a degooser, I'd say that if you took carbon and added it to water versus taking carbon and adding it to pH adjusted water, and then adding your metal, you get two different catalysts. You get two different catalysts that perform differently, and there's lots of data to support that and explanations. We're taking a completely different approach where, like in a slurry system, you don't have to worry about filtration. You don't have to worry about disposing of the water. Basically, you have that material now as a cake, and you can run it through whatever process you want. The other thing is, you have the opportunity, I think, though we haven't demonstrated this yet, to create bifunctionalities in catalysts in a much easier manner. And also, depending upon the type of colloidal material that you use, okay, you have the opportunity to impact on the porosity and surface area. And I might also add that, we do believe, and we've also, demonstrated this to a certain extent, that you can take nanoscale particles and incorporate them into a matrix like this, and they're much easier to manage, and obviously you see the enhanced performance.
Any other question? It's all this time.
Thank you.